This one's a cooling model. A thermometer is taken from an inside room to the outside, where the air temperature is 5 degrees Fahrenheit. After a minute, the thermometer reads 55 degrees, and after 5 minutes, it reads 30 degrees. What was the initial temperature of the inside room? I think a visual is useful in this case. Here I've got a lowercase t axis for time and an uppercase t axis for temperature. And the idea here is we've got the outside temperature is 5 degrees Fahrenheit. So I'm going to just draw a horizontal line that I'm going to label it 5 degrees Fahrenheit. We don't know what the temperature was inside the room, but the thermometer was taken outside and it started cooling off. After 1 minute, the temperature is on the thermometer is 55 degrees. And after 5 minutes, the temperature of the thermometer is 30 degrees. For our model, the 5 degrees outside is the temperature of the medium, or the surrounding temperature. Speaking of our model, it is dt is equal to k times t minus t sub m. Let's solve this. You'll note this is also separable and linear. And I'll tell you, I've tried to explain this both ways, and separable is so much easier. So we're going to go with that. dt divided by t minus t sub m is equal to k dt. So the natural log of the absolute value of t minus t sub m is equal to k times t plus a constant. Exponentiating both sides and using properties of exponents, as I've done several times throughout this course, we're going to get that t minus t sub m is equal to, I'm going to call this dE to the kt. And in fact, I'm going to call it d sub 0. Finally, we get that the temperature as a function of time is equal to the surrounding temperature t sub n plus d sub 0 e to the kt. That d sub 0 that we see in the equation is actually the initial temperature difference. Over in our graph, that would be represented by the distance between the initial temperature and the surrounding temperature. We can see in our model that if t is 0, then the temperature we have at 0 is equal to the surrounding temperature plus d naught. Hopefully that's convincing enough to tell you that d naught is the initial temperature difference. Since it's the initial temperature difference, we can actually represent it as t sub 0 minus t sub m and update our model. So temperature as a function of time is equal to t sub m plus t naught minus t sub m, that quantity times e to the kt. Since we know that t sub m is equal to 5, we now have t of t is equal to 5 plus the quantity of t naught minus 5 e to the kt. We have our earlier information. After 1 minute, the thermometer reads 55 degrees. After 5 minutes, it reads 30 degrees. And then the initial temperature is what we're looking for. I'd like you to use that information to go ahead and answer the question, what is the initial temperature of the inside room? At 1 minute, we have 55 degrees. At 5 minutes, we have 30 degrees. I'm translating that into t of 1 is equal to 55 and t of 5 is equal to 30. Since t of 1 is equal to 55, we have 55 equals 5 plus the quantity of t naught minus 5 e to the k. And since t of 5 is equal to 30, we have 30 equals 5 plus t naught minus 5 e to the 5k. Subtracting 5 from both sides of both equations gives us two equations. 50 equals the quantity of t naught minus 5 e to the k, and 25 equals t naught minus 5 e to the 5k. Dividing the first equation by the second equation gives 2 equals e to the negative 4k. Solving for k gives us an approximate value of negative 0.1733. Substituting that into the equation where we had just k in the exponent, so the 50 equals T naught minus 5e to the k gives us that T naught, the initial temperature of the room, is about 64.5 degrees Fahrenheit.